In this circuit diagram, we need to find the equivalent inductance of the two inductors in the figure. We also need to find I of t when t is 1 second. We are told that when t is equal to 0, we have this I1 and I2 here. We also have a voltage across all parallel elements, which is this, for when t is greater than 0. So the first thing we're going to do is find our equivalent inductance. We know that inductance acts like resistors, in that if they're parallel for resistors, inductance are going to act the same way in parallel. And if they're in series, inductors are going to act the same way as in series. So when we look at these two inductors, we only have two. We have this 4 henries and this 16 henries. So we can plug them into the inductance for parallel formula, and we get 3.2 as our L equivalent. So this is going to be our inductor equivalent, 3.2 henries. Now we need to find current, so we're going to use the current formula. As always, this can be found linked in the description in the notes, section 6.1, the inductor. Now we do know a few things. We do know our 1 over L. This is going to be 1 over 3.2. We just found our L equivalent. This is 3.2 henries. We also know this I of L at time 0. At time 0, we have these two I's right here. And we know that because it's in parallel, we can say that this current is going this way, and this current is going up this way. So they all come to a single node. And this current, our I of t, is going out this way. So basically our I of t is going to be the summation of our I of 1 and I of 2. If we add our I of 1 and I of 2 together, we're going to get a negative 5 amps. So this is going to be negative 5 amps. I of t at 0 is negative 5 amps, and we want to find I of t at 1 second. This is why we're using the integral. We know that our voltage is 64 times e negative 4t volts, so we're plugging this in here. We're going to bring out our 64 from the integral because it's a constant. So we're going to take our 64 and then divide it by the 3.2. In doing this, we are going to get 20. And then we can also integrate what's left inside, which is the e negative 4t. And we know that when we integrate this, we're going to get e to the negative 4t over negative 4. And then we have our closing brace. So we have the 1 and 0, which we will be integrating. I'm also going to factor out the negative 4 just so it's a little easier. So when we write this, we're going to have a negative 5 amps plus 20 volts over 4, which is actually going to be minus 5 volts. And I guess when we take the derivative of this, it's going to turn into amps. That way we can add them together. And then we have the parenthesis with e to the negative 4 minus e to the 0th power. We know that this is just going to be 1 because anything to the 0th power is 1. And now we can plug the rest of this into a calculator. And after carefully plugging this into a calculator, we're going to get negative 0.0916, and this is in amps. So this is our I at 1 second. Now we want this in milliamps, so we're going to convert this by multiplying the top by 1 milli and dividing it by 10 to the negative cubed. If we do this, we're going to move the decimal 1 to 3 over, and then we're going to get that our answer is 91.6 milliamps. And this is a negative. We cannot forget the negative, which we have right here. So that's how you would go about solving this problem. If you have any questions about the material covered, you can leave them in the comments below. If you want more introduction to circuit analysis, there's a playlist as well as notes in the description.